Hello, this next video in a playlist that I'm calling Introduction to Mathematical Statistics, and we're in chapter 4, part of this playlist I'm calling Joint Distributions. And let's jump to today's topic, which is conditional density functions. So first we're going to give the definition of the conditional density functions, and then we're going to prove their densities, and then we're going to use it to find the best predictor of y given a function of x. So let's jump in. So let's let x, y be a random vector, and it can be discrete or continuous, and it has a joint density of f of x, and it has marginal densities of f of x and f of xy. Then the conditional density for x given y, assuming that the marginal density of y is positive, it's denoted by f of x given y, and here's a more detail of it. So f of x given y is the joint density function of x and y divided by the marginal of y. And this marginal normalizes it, so that becomes the new sample space of this joint density function. So x and y are arbitrary, so we could switch them. So the conditional density for y given x, assuming the marginal of x density is positive, it's denoted by f of y given x, so it's the joint density of f of xy divided by the marginal density of x. So it's whatever we're conditioning on. Now, to prove that they're densities, we need to show two things. The necessary and sufficient condition is that the density is always positive and that it integrates or sums to 1, depending upon whether it's continuous or discrete. So first, let's assume that x and y are discrete. Now, to show it's a density, 1, we have to show it's positive, and it is positive since the joint density is always positive, and the marginal density is always positive, and that means the ratio is positive. So that part is proven. Now, to show that it sums to 1, we just sum the density over all x, and since f of y, there's no index x in it, and come out front of the sum. And when you sum a joint density over all of one variable, that's the marginal density of the other variable. And then those cancel and it's 1. So in the discrete case, the way we define it here, it is a density function. So now let's assume it's continuous, and we want to show that the conditional distribution of x given y is a density. So we have to show it's positive, and it is positive since the joint density is positive and the marginal density is always positive and the ratio is positive. So it is positive. So that's the first condition. And the second one, it has to integrate to 1. So if we integrate, oh, that should be a space. So I used the wrong slash in LaTeX, and so I'll fix that. So we're integrating over all x, so the f of y can come out front. We're integrating this joint density over all x, so that's the marginal of y, and then that ratio is 1, so it is a density function. And again, the paper version will have that corrected. So now let's interpret what we have, and in the discrete case, it's very easy. So the joint density, we defined it as this, the f of xy over f of y, but really those are probabilities. So this is equal to the probability that a random variable x equals some value x, and a random variable y equals some y divided by the probability that y is equal to y. And this is just a statement of conditional probability. So the conditional density in the discrete case is really the conditional probability. Now in the continuous case, it's a little bit different because you can't talk about the probability of a point, because that's always 0 in the continuous case. So we have to talk about neighborhoods or intervals. Neighborhood is a math term that means a really small interval about a point. So in the continuous case, let's let x1 and x2 be positive scalars. And let's also assume that x and y are continuity points of the joint density and the marginal density. And let's look at this probability. Now the conditional probability that x1, I could just call it x, dang it, is in this interval, given that y is in this interval, and we're going to divide by h1. Now the conditional probability is the joint probability divided by the marginal probability. And then we're adding a well-chosen 1, H2. And these probabilities, this numerator creates a rectangle, and then that can be solved using the cumulative distribution function as this. And I'll let you work that out, but this does create that probability of that rectangle of this statement. Again, we're dividing by H1 and H2. This, of course, is just the difference of the cumulative distribution functions and then divided by H. Now, if we let H1 and H2 go to 0, then the denominator here is the marginal density of f of y. And this numerator goes to the joint density of x and y. And this is what we were defining as the conditional density of x given y. Now we started with this, so if we multiply the H1 to the other side, which is this, then that gives us a way to interpret this. So thus for small h1 and h2, the product of h1 times this density value, remember it's not really a probability, it's just a density value. It's approximately the conditional probability that x, I don't know why I keep putting x1 there, lies in a small neighborhood of x1, and that y, should be y, not x2, lies in a small neighborhood of y, not x2. And so that's the basic interpretation. And I'll correct these in the hard copy. When I'm done with this playlist, I like to put them out there for people to have. Now let's look at the best predictor of y using a function of x, call it g of x. Now best means according to squared loss, so the average squared loss. Now in a video I have called Best Predictors of Y using a function of X, I show that G of X is actually the expected value of Y given X. That's the solution. Now, unless this random vector is a bivariate normal, this expected value can be pretty complicated. It can be a complicated nonlinear function. And so in many cases, we don't use that. We restrict our g of x to be a line. It's a linear predictor. So the best linear predictor of y, assuming we restrict g of x to be some sort of linear function of our x, then it's this. And again, in that same video, Best Predictors of Y using a function of X, I show that the solution to this, and show means I take partial derivatives, I solve it, and then we find that the solution of alpha is this. So that's the mean of Y minus the correlation of X and Y. Those are the ratio of the standard deviations times the mean of X. The beta is this, so it's the correlation between X and Y times the ratio of the standard deviations. Now, as a quick example, let's let the joint density of X and Y be 8 times X times Y, where X is between 0 and Y is between X and 1. And then from this, we derive the marginal density. So f of X is this expression and f of Y is this. And once we have those marginal densities, we can find the expected value of each of those. So expected value y is 4/5, expected value of x is 8/10. And the reason we're doing that is we're gonna have to fill it in for this, these values here to find the best line. The variance of x is 2/75. Variance of y, variance of x is 11/225. The covariance between the two is 4/225. And then the conditional density of y given x, so that's the ratio of the joint density divided by the marginal. Notice it's this. And now we can find the best predictor. So if we take the expected value of this with, in regards to y, we get this expression here, 2/3 times x squared plus x plus 1 over x plus 1. So this is the absolute best predictor of y using a function of x. The best linear predictor would be this. So we plug in we put these values in for alpha, and beta, and we get this expression. Now I'm going to use R to plot these two functions to show you what they look like, and this is it. So look at the black line, that's the best predictor of y given a function of x. And the red line is the best linear predictor of y given a function of x. Yep. Okay, well, we're right at 10 minutes, so I'm going to stop this video, and I think the next video deals with transformations of random variables. And hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.